Hello, welcome back. This is the final summary for the analysis 1 and 2 about the folder system, the files, and the directories. We talked about zero as not being nothing. Zero means something because zero helps us to define um, any number, because when we put any number raised to the power of zero, we get one, and one actually is very important in defining or identifying any numbers. Any number to power one, it is that number. So we looked at that when we're trying to talk about the international system of numbering, and we discovered the place values of numbers beginning from ones, as you can see, ones, tenth, 100, 10,000, 100,000, 1,000,000, etc., etc. And those are the international system of numbering according to the standard. So we look at folders, files, and directories as being all about the storage system. When you think of hard drive, memory, whatever external devices you may have, in terms of their appearance, just see them in terms of them having files, folders, and directories inside them and nothing else. So um, the state of the system is defined by the binary bits. When the system state is set to zero, that means the system is off. And when the state is set to one, that means the system is on. So data, to exist physically in the digital world, its state must be on with the value 1 as a unit of information, not unit of measurement, the unit of information in the system. So this may suggest that um, anything that exists physically must explicitly exist with some sort of measurement in the system or some sort of state in the system. The system recognizes it in terms of bits. Like if the state of the system is set to one, that means something is physically, present in the system. And if the state is set to zero, that means that thing is either dormant or doesn't exist in the system. Now, this actually is the case with the researches that have been done to try to find the natural storage devices by using biological means. The issue with that will be in the access methodology and manipulation of the biological system by using different kind of methodologies. I don't know the feasibility of that because if something exists naturally, uh, it must exist physically. So if we know the physical properties of the natural existence of those biological system, then that will define the limitation of their existence. And that may not be an absolute solution to the problem we have for the storage system. So we looked at the fallacies, in the digital world. Um, Everything in a computer is presented at the level of bits, and bits are the digital uh, system. They define the digital system. They are derived from the binary systems. So the fallacy in bits people look at bits as the storage unit of 0 and 1, but in fact, it is a unit of information, the smallest unit of information that the processor can process. And another fallacy was on byte as being 8-bit, which is true, but it's not enough. If you say byte is 8-bit, it's true because 8 bits is the content of 1 byte. But it would be nice if you could say that byte is a standard for encoding a character by using 8 bits. That is complete. And then a kilobyte. Kilobyte is not 1000 bytes. It is 1024 byte. And it came as a result of the base 2 system raised to the power of 10. And the 10 that is raised up on top of 2 is actually the bits required for arranging the characters in the system. So that is it. So the actual value of data in the system in the binary digits is what is referred as bits. They are the basic unit of information that the processor deals with. And they are also used to define the state of the system, the on, the off state, the active state, the dormant state of the system can be defined by using those binary bits. Byte is the encoding standard for one character, for presenting a character, of data in the binary digits in the system using binary digits. So the content of byte is 8-bit, and kilobyte is also the encoding standard which is used to define the smallest size of memory that a computer system can have. And we also look at the integer. Any number raised to the power of 0 is 1, and any number raised to the power of 1 is that number. And then it continues from there. That's the power of 0 and 1. 0 and 1 define the beginning of all the numbers that we are aware of. But those numbers are not binary. They are not the numbers that the computer uses for communication. So we need to take note of that because computer uses binary numbers, which is base 2 system. And those binary numbers are the digits of the binary numbers. Those digits are only ones and zeros, which are, the elements of the base 2 system. You see, the highest number in the base 2 system is 1, and the lowest one is 0. That's why it is important in the communication. And ones and zero, as I said previously, are used to define the state of the system. So, other numbering system are base 10, which is the decimal system. We have octal, which is base 8, and we have hexadecimal, which is base 15. So I indicated it clearly that base 8 is not used in the digital world, but it's there for us to be aware of it. Actually, they have other uses somewhere else, but base 10, it defines a decimal number that we human being can understand, and hexadecimal base 15 are mainly used to define the addresses of the memory, the IP addresses, and many other characters definition in the system. So we talked about bits as being byte as being 8 bits, and a half of a byte is called nibble or octet. But you should not mistake that because 8 bits or 4 bits are under 10. Therefore, we call them that name. No, it's just a standard. So byte, 1 byte is equivalent to 8 bits to represent a digital character. You know, for example, a character of letter, numbers, symbols form to create a byte, which is a standard for encoding each character, by using 8 bits to represent each character digitally to the computer so that the computer can process our data. And the ASCII shows numbers from 0 to 127 to, to represent characters by using decimal representation, which is very easy for human being to understand. And they also use some hexadecimal ranging from 0 to 7F. They are all used to, to present or encode language elements like letters, one from A to Z, or numbers like 0 to 9. So this group of 8 bits can be kept, at a space of 2 raised to the power of 8, which gives us 256 position inside the memory. So 200 position is the number of ways that we can arrange a character. So think of 256 as the number of characters that can be available by using 8 bits in the system. And that's why we need bits. So byte came as a result of 8 bits, and kilobyte is 100 and 1024 byte. We use 10 bits to get a kilobyte. Remember, byte is the smallest addressable spot in the memory that the processor can access to fetch the information and processes those information bit by bit. And kilobyte is the smallest size or space of memory we can have for a computer to be able to do anything for us. For example, to display a page of document per se. So we use 10 bits to present a kilobyte, which is found by using the binary base 2 system. So when you put 2 raised to the power of 10, we get 1024 byte. So there are extra bits added there, 2 bits. One to define the beginning of the character, and the other one is to define the end of the character. That's why we have 10 bits to represent a kilobyte. So kilobyte is equivalent to 2 to 1024 byte, as you can see there, and that became the standardized minimum size of memory. The original name is called kilobyte, but not kilobyte. But according to the standard, kilobyte is acceptable because it's easy for human being to pronounce this, and it is a fallacy because, people are now used to this and they are forgetting the original name, and some people think that because 1024 is higher than 1000 by just 2.4%. Therefore, 1 kilobyte is equivalent to 1000 byte. That, my friend, is another fallacy, and that's the reason I marked it there. Remember, in the previous video, we had some errors there. I forgot to put that E there to make it fallacies. So I was meaning fallacy, which was like I was talking about some might, some kind of biological insect if you like, but that's not what I meant. I meant the fallacies, which is the error in the judgment or reasoning. Yeah, so the international standardizations, the international system of number help us to pronounce, to remember all these unit of measurements. And without knowing that they are fallacious, you know, but it's okay because it makes life easy for us. But you need to be aware of the exact thing behind it. Although we think of it in terms of 1,000, we should know that the exact value of byte of kilobyte is 1,024 byte. But the IA system allows us to understand it as 1,000, which is very easy to remember. And the scientific notation for that is 1 times 10 raised to the power of 3, which means that a byte is 1,000 of characters. For example, a page full of text, just a page. The three zeros there symbolizes the the three there symbolize the number of zeros in 1,000. So it is the smallest unit of storage, and it is presented by that 10 raised to the power of, 2 raised to the power of 10, because computer processes data using binary system. And then when you square that, you get megabyte. Megabyte is 1,024 kilobyte. Because kilobyte creates actually another base, and that base came from base 2. Uh, when you raise 10 to the power of 2, we will get 1,024. And that 1,024 is another base system, but it is a base system which is based on base 2 because it came from the bits and the binary base. So we can now use that base to continuously derive other storage sizes or the measurement of storage. For example, uh, 1,024 times kilobyte, we get megabyte. And then 1,024 times megabyte, we get gigabyte. It keeps on going on like that, until whenever we find that, wow, we have reached somewhere reasonable for us to stop, then we can stop there. So, like this 1,000 is also a base. So we will multiply everything by 1,000 to get the next level of measurement. For example, 1,000 times 1,000 is 1,000 square. 1,000 square means 1,000 times itself 2 times. That's why we get 60. This is the scientific notation, which imply that 1 megabyte is equivalent or can be approximated to 1,000,000 of characters. For example, a 1-minute song, if you like. So the same thing continues. That 1,000 times 1,000 square, we get 1,000 cube. And then 1,000 cube is equivalent to 1,000 times itself 3 times, which gives us 10 raised to the power of 9 as the scientific notation. And in terms of binary system, we have like 1,024 times the megabyte in order to get our gigabyte. So to make it easy for human being to understand, this international system of numbering makes it easy in terms of 1,000. So we can easily understand 1 gigabyte as being 1 billion of characters. But in real sense, it's more than that when you use the actual binary system. Like if you multiply 1,024 times 1,024 times kilobyte, which is 1,024 times 8, you will get a string of characters more than 1 billion, but it will be under 1 billion, obviously. So 1 billion of characters could be like a DVD video. It comprises of 9 zeros. So a billion has 9 zeros. So as we go on and on like that, we continue getting um, a different kind of measurement. You get 1 terabyte, you can get 1 terabyte, which is a trillion of characters, 1 petabyte, which is a quadrillion of characters, 1 exabyte, which is a quintillion of character, and 1 zettabyte, which is a sextillion of character. I remember I said somewhere that the NTFS system is up to uh, uh, um, 1 zettabyte. I think the largest size of NTF file system is up to 8 zettabyte, according to some research paper out there. So that's how big the NTFS file system is. It is used for the global data production. For example, according to some research, 33 zettabyte of data is used per year. So we produce 33 zettabyte of data each year. Now, if it continues like that, you can imagine the kind of space we may need for keeping our data. And you can ask yourself whether we have enough space or not. That is the largest space we have currently is zettabyte. But we can go beyond zettabyte to yottabyte, which comprises, if you can, of all the entire size of the internet. There are 24 zeros in yottabyte. And then we have what is called brontobyte, which comprises of 27 zeros. It is known as the octillion of characters. You know, these ones are now preserved for research purposes. And then we have the future generation storage space for exploring big data and artificial intelligence system, because we don't have any hard drive, which is equivalent to geobyte. So you can think of geobyte in terms of having 30 zeros. Just remember that you can write one and then 30 strings of zeros in order to get 1 geobyte. So, my friend, these are the standards organization who participated in defining and restricting the communication according to the standard. We have ASCII, which stands for American Standard Code for Information Interchange. They came up with the standard for encoding a character by using 8 bits in the system. And also they joined together with International Organization for Standardization and International Electrotechnical Commission. So altogether, they came up with what is known UNICODE. It's known as UNICODE. UNICODE is another standard for encoding data, which is wider than ASCII standard, because UNICODE gives us the capability of using up to 32 bits to encode a character in the system. But there are many encoding methodology between 0 to 36 bits in the Unicode system. It depends on the requirement of your data. You can have a Unicode code that may encode data by using 8 bits, 16 bits, 24 bits, up to 32 bits, depending on your requirements. So International Organization for Standardization enforces all kind of standard for communication that you can think of, up to defining the prefixes and the prefix specifier for the measurement of units. For example, they came up with O to symbolize octet, and octet, is just like the group of 4 bits. It's mainly used in the network, but we're not going to explore it now. And B for byte, K for kilo, just to avoid the ambiguity, they also came up with the International System of Unit. And the system of unit, you can think of them as those prefixes. They specify, like we have megabyte, gigabyte, terabyte, exabyte, zettabyte. All those are international unit system of units. And I've indicated somewhere that the state of the system is defined by the binary digits. One symbolizes the on state, and the zero symbolizes the off state of the system. And then if you raise any number to the power of zero, you will get one, and that one is not binary, it's the decimal number system. Or you can think of it in terms of integer, which is not the binary digit. So you cannot use that one to define the state of the system, because computer only operates at the level of bits, not at the level of decimal number or integer. So yeah, you will have to take note of that. We have looked at that. So the actual values of those bits, of those bytes, of those kilobytes, by using the binary system, can be found uh, while talking about the exact prefixes of those measurements. For example, a kilobyte is 2 raised to the power of 10, which gives us the exact number of character, in a page, because 2 raised to the power of 10 gives us 1024 times byte, which is 8, 8 bits, to get the exact number. So precisely, a byte is equal to 1024. A kilobyte is 1024 times 8 bits, which is equivalent to a byte, not bytes. And that is the actual name of what we call kilobyte. Is actually kilobyte. And the same thing applies to all other units of measurement. If you square 124, you get 2 raised to the power of 20, which gives us megabyte, and the actual name is megabyte, but we call it megabyte, So, those those are the fallacies in the pronunciation as well as in the meaning, because some people think of megabyte in terms of absolutely 1 million of characters or of data being processed by the processor. But in actual sense, it is more than that. That's why it's called megabyte. The same thing is applicable for gigabyte, which is called gigabyte. So that's the real name, gigabyte, which is 2 raised to the power of 30. So you keep on going on like that until when you get to the biggest size we have, which is 2 raised to the power of 100. 2 raised to the power of 100 is called geobyte, or there's even no standardized prefix for this one as yet, because as you can see, we have kilobyte, megabyte, gigabyte, terabyte is for terabyte, petabyte is for um, uh, petabyte, and xbyte is for exabyte, and zettabyte for zettabyte, and yobibyte for yottabyte. You see, so these prefixes makes it very hard for human being to pronounce and understand. That's why they came up with a shortcut of kilobyte, megabyte, gigabyte, terabyte, petabyte, exabyte, zettabyte, yottabyte. Instead of saying yobibyte, you can easily bite your tongue there. So, yeah, so the exact values are there, in terms of binary, you just start from 1024 and then just keep on multiplying it by itself to get 1024 square, then multiply by the base 1000 cube, 1024 cube multiplied by the base to get the next one 1024 raised to the power of 4 times 1024. You keep on multiplying it by the base to get the next one. Actually, that's the best way of remembering it. And that, my friend, define the measurement that the system can have for their storage, their folders, or their files and directories. Yes, the question is, do we have enough space? Well, we know that computer processes data in terms of bits and fetches data in terms of byte, which is 8 bits, and then store data in terms of kilobyte, which is 1024 byte. And from there, we can get all other, you scale up kilobyte to get other, other storage sizes. For example, megabyte, gigabyte, terabyte, petabyte, exabyte, zettabyte, yottabyte, brontobyte, and geobyte. So far, that is how far we can go now. But the question remains the same. Do we have enough space? That's why, I say yes, big yes, but the other side is a big no, because there's a growing worldwide demand for data to be explored by data scientists who are doing research, day and night. They're doing artificial intelligence system, coming up with artificial intelligence systems, and they're exploring big data, in the in the field of artificial intelligence using machine learning, which may require a huge amount of data for accuracy, and we don't have the space for those data. You know, that's why in the current storage mediums, capacities are not enough. In addition, the current systems are very costly because they consume a lot of physical space and require a lot of power, for us to use them. And because of that, they generate also a lot of heat, which may need a huge cooling system. And because of that, in trying to get the cooling system or electricity, you find that we are polluting the environment using carbon dioxide, which is emitted in the atmosphere, you know, and that create another problem. And the current system also has limited retention time. So there is need for better form of storage system that will have a good information density that can be durable and energy efficient and cost effective, storage with, a huge ultra density storage medium to meet this exponential growth in the demand for the data storage that we need to explore. The artificial intelligence systems and big data systems and many other areas of data science. There are many data scientists out there who are doing researches, but they're limited with the storage in order to explore big data. So we need, obviously, a new way of storing data. That's why many researchers are now trying to move from this physical storage medium to the natural storage, such as using the DNA, the bacteria, and proteins as the next generation information storage system. And you can find that in that paper written by Lin Bachia and the group. They came up with some finding. They said it is easy to move away from the current physical system, and then use some biological data storage in the living cell for storing the data, using our DNA, using the protein, using the bacteria, you know. All these will aim at reducing the cost, and eliminate the need for electricity and, the space. So, do we really need them? Well, that is a research question. Nevertheless, we need to use what we have got now to organize ourselves digitally while waiting for a scientific breakthrough. So, my friend, that's all about the storage. I believe now you have a good idea about the file systems, how the sizes of the file system help us, you know, and how to understand the the level of communication in the computer and how human beings understand, you know, some data. What computer obviously uses binary system, but human can easily understand data in terms of decimal system. And then there are standards organization that restricted the size of the memory to represent characters in the system. They came up with a way of encoding a character by using 8 bits. All those are very important in knowing about the system storage, files, folders, and directories. So I gave you some reference as you may be interested to know more about this natural storage of data. There's a paper, very interesting paper written about the random access DNA memory by using Boolean search in an archive file storage system. Another one is the DNA as a universal chemical substrate for computing and data storage. We also have another paper, and that's the one I referenced in that text that I am giving you now. Is a 10-year of natural data storage that they believe that in 10 years we would have um, the DNA, bacteria, and proteins as the next generation information storage system. And there are many other information that you can gather from those research papers. So I encourage you to go and read. And in summary, we talked about the demand and supply. You know, as I said before, um, kilobyte is a very, very, very important space that we have to master, because all other spaces scaled up from kilobyte, which is 1024 byte, and it is a standardized size of memory, and the actual name is kilobyte, but not kilobyte. That's why I call it fallacies. Please remember, I wrote fallacies in the previous video, but I found that there was a spelling mistake there. The E was left out, which made the whole thing to sound like I'm talking about some kind of a mite or something of some sort like that. But that's not what I meant. I meant fallacies, which basically the error in reasoning. So kilobyte is very important. All other measurements actually scale up from uh, kilobyte. So what is it about the demand and supply? Yeah, there's a lot of demand for data to be explored by data scientists, researchers. You know, the demand is actually increasing, because of the artificial intelligent big data systems, which may require a huge amount of data for accuracy. So the demand is increasing, but the supply of the storage is decreasing. So this is the principle of demand and supply. And those who are doing economics, this may be very interesting for you. You can even write a project about this, and then, talking about the demand and supply, the demand and supply of the storage devices. You see, the demand is increasing and the supply is decreasing, and that will affect the price. So you can do all sort of derivatives from this concept, in economics. You can talk about price elasticity of demand there. You can talk about a lot concerning production theory. Mix a lot of the principle of marginal productivity, and a lot of things can come out from there. But I'm not going to go in economics. I leave it for you there, those who like economics, but I'm trying to mix economics and ICT. Now, let us look at the current problems. Um, yeah, Currently, as we have seen previously, the current storage capacities are not enough. The current system are very costly. They consume a lot of physical space. They also consume more electrical power. They generate too much heat, which necessitate a significant cooling system. And also, they generate a lot of carbon dioxide actually in the atmosphere. We generate that in trying to solve the problem, and the system have limited retention time. So, what are the solutions? Yes, that's where there is need for better information density, like a good storage that will keep a lot of information that will last for long, and that can be energy cost effective. We need that right now because we don't have them. The one we have is causing the problem listed above. So there's need for different way of storing data to meet the exponential growth in the demand. So we need to increase the supply to meet the demand, because the demand now is higher than the supply. Well, there are ongoing studies. Many researchers are now trying to move from the physical storage medium to the natural storage, such as using DNA, bacteria, and proteins as the next generation information storage systems, moving away from the digital file system to biological data storage in the living cell. You remember that? Data will be now stored in the living cell. And how many living cells do we have in the world? A lot. So all that, will be aiming at reducing the cost, eliminating the need for electricity, and increasing more space, and many others. Nevertheless, I think we just need to take things easily, step by step, while waiting for that scientific breakthrough. So, my friend, that's it for the storage measurement. In the next video, we are going now to look at, how we are capable of organizing ourselves digitally, because now we know about the file, the folders, the directories, and for us to be organized digitally, we need to know how to make ourselves organized, in the computer, by knowing where to create the files, how to link them, where to put the folders, where to do. So it's all about organization. So we are going to explore the file management, how to manage our data using the file, how to create the files, and how to share files among us, especially when we are doing programming. For example, if you are a team, you are part of a team for software engineering, you will need to be sharing codes, sharing a lot of things, and all those depend on, managing file, which is very, very crucial in programming. So we are going to look at both local file management systems as well as the global or international. So the global or international one, I will, walk you through what is called Git. You need to learn how to use the Git and the GitHub and other resources out there in the cloud computing that you can use for sharing your files and sharing your project with others. Because in life, we need to work together with other people. They say there's no silver bullet in software engineering, meaning that you cannot do everything by yourself, or you don't have a solution that can fit all different kind of problems out there. So it is very important to work in a team, and that will require us to share our document, to share our files, folders, even directories. You see, there's only one directory for the internet, and the entire world is sharing it. That is how important the storage is in the world of communication, or in the digital world, or in the world of computing. And my friend, that's the reason why I am dwelling on this over and over and over again. I want you to have this at the back of your mind, that you cannot do without files, folders, and directories anywhere when you are faced with computer or any electronic devices, because you need memory to store data to be processed, to store the processed data, and to store the data that is being used. So if you don't have files, folders, directories, it will be impossible for even computer to do any work. My friend, that is how important the concept of files, folders, directories are. And that's the reason why I want you to get it right. So thank you for enduring up to the end of this video. Yeah, I've just decided to embed everything here for the storage, the measurement of the unit of storage, and I forgot to talk about the processing speed, but that depends on the kind of process you're using as well, because the speed of processor is measured in frequency, and the rate of frequency is called hertz. So the processor is measured by using hertz, and we use bits per second as the prefix, for uh, the speed of the processor. So if you've watched the previous video, everything is there. I explain everything there in those small bits and pieces. This is just a block of video to summarize everything concerning units of measurement. So thank you for viewing and happy learning. My name is once again Samuel Ambrose Onen, a BSc and MSc holder of Advanced Computer Science from one of the most prestigious universities in the world. I'm a researcher myself. I will be happy to see your comments. Please give me a thumbs up or thumbs down, because why not? I like constructive criticism. So just feel free to give me your view concerning what we have discussed here. Thank you. I'll see you in the next video.